Electric fields have so many applications in motors, touchscreens, biology, and medicine. First, let's learn some history about it. Michael Faraday's work was inspired by that of Hans Christian Ørsted, who discovered that electricity produces a magnetic field. In 1820, he observed that a compass needle moved when placed next to a current flowing through a wire. Michael Faraday further refined and developed these concepts later that century with an induction experiment.
By inducing a current in copper wire with a magnet, Michael Faraday further explained the interrelation between magnetism and electricity with the idea that magnetism can induce an electric current. This electric field between charged plates involves the flow of ions between two oppositely charged plates. The generated field poses many great applications, one of which is a process of gel electrophoresis.
Before we begin to analyze the mechanics of gel electrophoresis, we first need to understand the basic principles behind it. Physicists wanted a way to explain the interaction between charged particles when they weren't in contact with each other. The concept of the electric field was used to explain this phenomenon. A charged particle creates an electric field which exerts an electric force on surrounding particles. It's important not to confuse electric fields with an electric force. An electric field exerts electric force but is not equal to it.
A positive charge creates an electric field radially outward. On the other hand, a negative charge creates an electric field radially inward. The electric field is conventionally represented by arrows pointing towards a negative source charge and away from a positive source charge. With this model of a source charge and a test charge, the strength of an electric field is defined as the electric force on the test charge per unit of charge.
Coulomb's law explains the electric forces between two charged particles in terms of their charges and the distance between their centers. Substituting this formula for electric force in the electric field equation gives that electric field strength is equal to the product of Coulomb's law constant and the charge divided by the distance squared. The equation shows that electric field strength is inversely proportional to the separation distance squared. Therefore, field strength decreases as you get farther from the source. We can then use this formula to determine electric field strength at a certain distance from the source charge. For example, what is the strength and direction of the electric field 3.74 centimeters on the left-hand side of a 9.1 microcoulomb negative charge? To solve, convert the given measurements into their SI units. Then plug them into the equation for electric field strength. The answer is 5.855 times 10 to the 7th newtons per coulomb, to the right.
Charged particles are influenced by nearby electric fields. A positive test charge will be repelled by a positive source charge, moving in the same direction of the electric field lines. On the other hand, a negative test charge will be attracted by a positive source charge, moving in the opposite direction of the electric field lines. Electric fields can also be created by other charged objects such as parallel plates. The electric field between two charged plates is an example of a non-contact force. The charged plates disrupt the area between the plates, creating the field.
So how do the characteristics of these plates affect the electric field? There are two factors that affect electric field strength: plate separation and voltage. As plate separation increases, the electric field strength decreases. In contrast, the electric field strength increases with the magnitude of the potential difference of a battery. The sign of the potential difference determines the direction of the electric field as the plates switch polarity. It is this electric field that enables gel electrophoresis. Gel electrophoresis is a process that researchers can use to select a particular size of deoxyribonucleic acid, or DNA, for their experiment.
In gel electrophoresis, a gel is set in between two charged plates. This creates the electric field between the two plates. Due to the presence of phosphate groups on the molecular structure of DNA, DNA is a negatively charged molecule. As such, when it is placed on the negative end of the electrophoresis system, the DNA will travel through the gel to the positive end. Agar is a substance derived from seaweed. When an aqueous solution of agar and water sets, the agar forms a sieve with uniformly sized pores. The higher the concentration of agar, the finer the pores.
The pores impede the flow of DNA, so smaller strands of DNA flow faster through the gel than larger strands. Therefore, with the same amount of current applied for a constant amount of time, shorter fragments of DNA with fewer nucleotides migrate faster towards the farther positive end than longer strands of DNA. To perform gel electrophoresis, DNA samples with a colored dye are pipetted into wells on the positive end of the gel. Current is then applied and the strands migrate, creating bands located at different parts of the gel. A molecular standard or DNA ladder can also be placed into one of the wells to compare size of the strands.
Researchers use gel electrophoresis in order to isolate the DNA they need to use in their experiment. Once the DNA is purified in this way, the researchers can sequence DNA or apply their use in various other biotechnological processes. Being able to compare the lengths of DNA fragments can be used in forensic sciences. As the DNA migrates, the bands from each well can be compared to each other to look for similarities or differences that may aid in forensic conclusions. Bands that travel the same distance are the same size.
Additionally, gel electrophoresis is an important stage in DNA sequencing. After DNA is amplified using polymerase chain reaction, an important step is the purification of the PCR product. One approach to this purification is aided by gel electrophoresis. Another type of electrophoresis that is based off of the migration of point charges across electric fields is called capillary electrophoresis.
Instead of DNA migration through the pores of a gel, it migrates through a fine capillary. Before DNA is placed into a well for analysis, it is combined with microsatellites that bind to a specific sequence of the DNA. At the end of the capillary, there's a detector that senses these markers and sends the data to a computer. This data enables the creation of electropherograms that show where the markers are located in the DNA sequence. Additionally, comparing the location of the microsatellites can help conclude if two samples are related or come from the same source.